Hey, good morning, everybody. And today we're going to do gas laws. Now, many of you studied gas laws back sophomore year in chemistry. Others of you continued on junior year doing more gas laws. Turns out they're really pretty easy as long as we have a good picture of molecules in motion in a container. So if we do that, I think we can handle these problems pretty well. What I'd like to do is a little bit of notes, and then maybe take a look at the first 4 examples to start, and then get into the ideal gas law. So if you could, take out a nice clean sheet of paper. Don't you miss that. And can you start writing down these notes with me? I've already written these out, so I'm just going to use what I've got. When it comes to gas laws, how molecules behave in a closed container, there are 3 ways that we can define those molecules and define their behavior in a closed system. First is known as Boyle's law. Well, maybe before we get to what it is individually, I want to take a moment to look at this beautiful picture that I've drawn in the past. So here we have a container. Now the container has fixed edges, but it has a movable piston. And this is the part that, if I don't say it out loud, sometimes people don't realize this part here. The piston can move in certain situations. Now, we represent what the pressure is by looking at what mass is placed on top of it. So right here we have a mass. Now, let's think about it. What are the forces involved on that mass? That's right. I'm going to have mg down, and I'm going to have the force of the gas pushing up. I'm going to even just write that as force of the gas. Now let's think about that. Force of the gas? What? How do we even handle that? Well, I know that pressure equals force divided by area. So we could think of it in terms of the pressure exerted by the gas would be the force divided by the area of the piston. All right. The thing I wanted to catch, you guys to catch, is that is a picture of a piston that can move up or down. And sometimes it's fixed. So, gas laws. Boyle's law tells us that the volume of a gas is inversely related to its pressure. V is proportional to 1 over P. Charles' law tells us that the volume is directly proportional to the temperature, and Gay-Lussac's law tells us that the pressure is directly proportional to the temperature. So what that tells me is that PV is proportional to the temperature. But this is the part I got to make sure you guys are good with when it comes to AP Physics 2 and how to solve problems. If I were to take this formula, or this relationship, P times V is proportional to temperature, and I would just divide by temperature, what I would get is that remains constant in a closed system. Oh, I already wrote that right here. PV divided by temperature is constant for a closed system. Closed system means that the same number of molecules that exist at the beginning of gas exist at the end. Okay, so what does that mean? Well, if we have a gas and we take it through a thermodynamic process where somehow we either change the volume, the temperature, or the pressure, if it's a closed system, then P1 V1 over T1 is going to be equal to P2 V2 over T2. That is the key. Honestly, if you fall asleep for the rest of this lecture, if you get P1 V1 over T1 equals P2 V2 over T2, you got it. There's only one catch, and that catch is that the temperature has to be in Kelvin. And if you think for just a moment, of course you're going to see that. If you were to plug in 0 degrees right here for temperature, what would you end up with? You'd end up with no solution, right? So that is obviously stupid. What you've got to do is you've got to make sure that in this relationship, your temperature value has got to be made in Kelvin. Check. P1 V1 over T1 equals P2 V2 over T2. Temperature's got to be in Kelvin. Say it. Nice job, David. Now, when we look at different processes, here's some vocabulary that came up in the PhET simulation that you did last class. Also, we're going to be using them all the time in thermodynamics. And the first, an isothermal process. Isothermal. What do you think stays constant? Temperature. Check. Isobaric. Well, we use a barometer to measure pressure. So isobaric process, the pressure stays constant. And lastly, isometric, the volume stays constant. Now, there's some other words we might use for isometric, old words. We'll deal with that when we get to it. So, take out your calculator. Take out this worksheet titled Gas Laws Examples. And let's bang through them. So, gas laws. Gas laws examples. Before we begin, what's that say? BRIN. No. What does that say? That's right. Brinkelhoff. And what does Brinkelhoff mean? Well, back from chemistry, maybe you remember, maybe you don't. It means that these are diatomic molecules. Meaning, when in a gaseous form, bromine is always going to be Br2. Iodine, I2. N2, Cl2, hydrogen, oxygen, and fluorine are all going to be 2. They're all going to be together. Now, moving on. A 50 cc. cc stands for excuse me. 50 cc. cc stands for cubic centimeters, which is also equal to a milliliter. Syringe is filled with air and the end is plugged. It is now a closed system. If the initial pressure on the walls of the container is 1 times 10 to the 5th pascals, when a force is applied to the syringe, the volume, when a force, if the initial pressure on the walls of the container is 1 times 10 to the 5th, when a force is applied to the syringe, the volume decreases to 20 cc's. Assuming no change in temperature, what is the pressure in the syringe? Well, I can't read, but I can do math. So, what do? Say it. Say it. That's right. Draw a picture. Now, drawing a picture when it comes to thermodynamic processes may be the most important time of the entire year to draw a picture because it allows you to keep track of all the information. So here is our first, what are we calling this one this time? A syringe, right? And if I were to pull together my information, P1 was 1 times 10 to the 5th. Josh, slow down. Slow down. I know you know how to do these. Big deal. They're easy. We're just building. We're building. V1 is going to be 50 cc's or 50 centimeters cubed. And then it goes through a thermodynamic process such that the volume becomes less. So how do I draw that? I'm going to draw the piston. And again. Now, it says no change in temperature. So T1 is going to be equal to T2. So pressure 2 is what we're looking for. Volume 2 is 20 centimeters cubed, and T2 is the same, constant. So, ready? P1 V1 over T1 equals P2 V2 over T2. Because the temperature doesn't change, I'm solving up for P2. Go ahead, let's do it. So P1 V1 over V2 equals P2. Now, you guys know when it comes to units, I get a little paranoid. Here's the thing. Let's just plug the units in this time as we punch it in. So 1 times 10 to the 5th pascals. Now, volume 1 is going to be 50 centimeters cubed, and volume 2 is going to be 20 centimeters cubed. In this case, because the units are the same, they cancel out, and I didn't need to do a conversion. That's good. So I get, for pressure 2, I get my calculator out. No, just kidding. Don't get your calculator out. That's too easy. I believe the answer is going to be 2.5 times 10 to the 5th pascals. Good. All right. That was easy. Would you guys take a moment and read number 2? Ready? All right. Let's try number 2. Ready? It says a 1-liter soda bottle with the volume given is filled with carbon dioxide. The pressure inside the bottle is 101 kilopascals when at 18.33 degrees Celsius. If the bottle is then placed in a bath of ice water, 0 degrees Celsius, what will be the pressure inside the bottle, assuming the volume stays constant? All right, let's give it a shot. Let's draw a picture. Now I could draw a soda bottle, or I could just draw the same container. Pretty much going to draw all unit. There it is. Now in this case, it said that the volume didn't change. So this is going to be isometric. I'll show that piston in the same position. Go ahead and draw in my molecules of CO2 that are moving around. Check. Let's pull the information out of the problem. So pressure 1 is 101 kilopascals, or 101 kilos, so times 10 to the 3rd pascals. It's just another way to write atmospheric pressure. Volume is the 1 liter, and the temperature is 18.33 degrees Celsius. Now, pressure 2 is what we're trying to find. The volume remains 1 liter, and the temperature is 0 degrees Celsius. So it's a closed system. So in some ways, this is a pretty easy problem. Actually, it is an easy problem. P1, V1 over T1 equals P2, V2 over T2. Volume stays constant. And what I'm trying to solve for, again, is P2. So I get that all alone. And I'm going to have P1 times T2 over T1 equals P2. Why? Because algebra says so. Now, I go and plug in my numbers, and I'm going to have 101 times 10 to the 3rd pascals over 0 degrees Celsius and 18.33 degrees Celsius equals pressure 2. So pressure 2 is going to be 0? Is that right? No, it's not right. Brady, what's wrong? Yeah, you're right. I just earlier said that the temperature's got to be in kelvins. So even though the degrees Celsius would cancel out, I still need to convert it into kelvins so that it's on the proper scale. So that you guys are so nice to just let me do that, even though I knew as soon as I started writing it that you knew that was wrong. So 101 times 10 to the 3rd pascals. Now to convert that, it's going to be 273 plus 0, I know, divided by 273 plus 18.33 equals P2. Get your calculators out. Anybody else get that the pressure dropped to 9.46 times 10 to the 4th pascals? Or I could write it as 94.6 kilopascals. Did you guys get that? Nice, good. What was the point? It's got to be in kelvins. Next. Because I was setting up to do the problem, and what do you know? It's a bad problem. Whoever made up this worksheet, some version of myself, probably at the age of like 34, didn't include the temperature of the gas initially. So you can't solve it. Life goes on. Turn the page. Number 4. This is the last one for now. We're going to introduce an important point here. This says a container of nitrogen gas at STP is sealed and then raised to a temperature of 573 Kelvin. Assuming the container's volume does not change, what is the pressure of the gas? Well, before we can do that, we need to talk about what the heck is STP. Now, I bet you remember that this stands for standard temperature and pressure. Now, what is standard temperature and pressure, you ask? Good question. For temp, we could say that it is either at 0 degrees Celsius or 273 Kelvin. Standard temp is 0 degrees Celsius, the freezing point of water, which if we are measuring things in the Kelvin scale, which we often are in this unit, is going to be 273 Kelvin. When it comes to pressure, there are some rounding issues here, but often we can use 1 ATM, and the AP Physics 2 exam actually uses 1.0 times 10 to the 5th pascals. Often it can be written as 1.01, or even better, 101 kilopascals. But we're just going to use that. So, standard temperature and pressure. Now, room temperature is 293. And some of you have that number stuck in your head from chemistry class. It's not room temperature. Standard temperature and pressure is at 273 Kelvin. So, we've got nitrogen gas in a sealed container, and it raises the temperature to 573. Assuming, let's draw a picture. So, here's my gas initially. Here's my gas at 2, where the pressure is 1 times 10 to the 5th. The volume, isn't changing, because I don't have room to put it in anyways. But the temperature is 273. Why don't you guys go ahead and solve this up while I'm working. It's all falling apart. No, solve it up. Keep going. Jake, you still awake? Oh, good. Thanks. What's the new pressure? P2. T2 is going to be 573. Oh, so it's just this. P1 V1 over T1 equals P2 V2 over T2. When it's a closed container, the math is super simple. P1 V1 over T1 equals P2 V2 over T2. Make sure you're in Kelvins. Question says it's at STP. There you go. Finish plugging it in. Solve it up. Thank you guys. Stay tuned for more.